So welcome to Exploration Research Virtual Institute class on the origin and evolution of the moon. This is our 14th class, the last class of the semester. My name is Jim Head at Brown University, and together with David Kring at the Lunar and Planetary Institute, both SSERVI centers, we are very happy today to bring you Apollo 17 astronaut Harrison H. Jack Schmitt to talk to us about the future exploration of the moon, the road ahead. 46 years ago today, on December 19, 1972, Apollo 17 splashed down, bringing an end to the fabulously successful Apollo exploration program. In that module that landed in the Pacific Ocean was Jack Schmitt and his colleague, Gene Cernan. Gene and Jack explored the Taurus-Littrow region of the moon and did a beautiful job of bringing back incredible numbers of samples and also doing a geological perspective on, indeed, a phenomenally interesting landing site that encompassed most of lunar history. Jack Schmitt was educated in the California Institute of Technology, receiving his bachelor's degree in 1957, and he had a Fulbright in Norway, studying at the University of Oslo from 1957 to 58. And he received his doctorate in geology from Harvard University in 1964. Jack has won a number of NASA Distinguished Service and Public Service medals, as well as the G.K. Gilbert Award in Planetary Geology, and a series of honorary degrees, as you might expect. Before joining NASA, Jack was with the U.S. Geological Survey's Astrogeology Center at Flagstaff, Arizona, working with Gene Shoemaker and many other the famous icons in geology, so to speak. And he was project chief for the Lunar Field Geological Methods and participated also in photo and telescopic mapping of the moon. In fact, Jack is the author of the Copernicus Quadrangle of the Moon, a classic geological map. Jack's also a pilot. He's logged more than 2,100 hours flying time, of which 1,600 of those are in jet aircraft. And he was selected to be a NASA scientist astronaut in 1965. And one of the major things that Jack brought to the program was not only his scientific expertise as a scientist astronaut, his geological expertise in exploring the moon, but also in essentially helping to educate not only his fellow astronauts, but also the engineers in mission control and operations director and throughout the program, and the managers as well at NASA headquarters. Jack was really the go-to person for, what exactly are we going to be doing on the moon, and how do we get this science and engineering synergism to work really well. Many a time was spent in Jack's apartment in Houston, and plotting late into the night about how to do unusual things, different things, maybe meet and land on the far side of the moon using a relay satellite, et cetera, et cetera. And Jack really was monumental in getting Lee Silver into the program to help train the geological aspects of the astronauts, et cetera. Jack, indeed, during Apollo 17 with Gene Cernan, again, it was the longest surface extravehicular activities is 22 hours, 4 hours, 22 hours and 4 minutes, and also they returned 115 kilograms lunar samples, and not only did he do that, but the discussions and further development of the geology of the Taurus-Littrow site has proceeded extensively in the period since that time. Jack has been extremely active in continuing to look at the samples, attend all the lunar science conferences, and really participate in the helpful analysis of the treasure trove of material, not only from Apollo 17, but the rest of the Apollo sites. Jack was elected to the United States Senate in 1976, and he went on to a distinguished career there. Today he is on Vice President Pence's National Space Council in the advisory group. And just to conclude in Jack's introduction, if you ever wondered why it is important to send humans to the moon, and indeed humans and scientists, you have no further to look than Apollo 17 lunar module pilot Jack Schmitt. Jack, over to you.
Well, thank you, Jim, and congratulations to you for this series, you and Dave Kring, and it really is remarkable. I've looked at a few of them, and I just think you guys are doing a great job to educate the next generation, as well as give the older generation a chance to talk. And as you mentioned, today we ended the Apollo lunar program, December 19th, 1972, with a splashdown not too far from Samoa in the South Pacific. It's unfortunate that beginning with the Johnson administration and confirmed by the Nixon administration, we only bought 15 Saturn V's. Maybe the pressure of having more of them would have meant that we would have continued to explore the moon and done many other things with that remarkably robust system. Let's see here. I think I have to do that. There we go. Well, we're going to talk about future exploration and what the road ahead might be. But first, I want to just bring you everybody up to approximately the same level in what that Apollo space program actually was. It certainly was something, the groundwork for which was laid by President Eisenhower in 1958 and 1960 timeframe. It was a bipartisan effort on the part of both Lyndon Johnson in the Senate and Congressman McCormick in the House to try to meet the Russian, then Soviet challenge, which was well recognized in a bipartisan way. And now, landing on the moon was first proposed, of course, by President Kennedy in 1961. It was to counter those Soviet advances in human spaceflight that most people, I hope, are well aware of, although I don't think the history of space is taught well in the schools of the United States anyway, maybe elsewhere that's taught well. It was a major competition, however, and we tend to forget that sometimes. It was a major competition within the Cold War, and in that competition, John Glenn sort of led the way for human spaceflight by orbiting the Earth in February of 1962. You probably are aware we just passed the 50th anniversary of the Apollo 8 mission, which orbited the moon in December of 1968, and indeed would have still been in orbit at this time, or nearly around Christmas time. But a major and important lead up to it that tends to get overlooked was Apollo 7. Apollo 8, the creature more or less invented by George Low, would not have flown. The primary constraint on flying, at least at the time it did, was that Apollo 7 be a successful checkout of the Apollo spacecraft. Same type of spacecraft that would take us on to the moon with Apollo 8 and with other missions. Neil Armstrong then successfully landed on the moon on July 20th, 1969, which in most people's mind at the time, I think, ended the moon race. Subsequent discussions with Soviet emigres and further analysis probably illustrates that the moon race really ended with the successful launch of the first Saturn V. Clearly, that was something, the primary enabling technology for landing on the moon, for even getting to the moon. And once the Soviet leadership had seen that happen, we are told, and I think it's safe to assume, that the moon race had ended. There were 5 additional Apollo missions that landed on the moon between November 1969 and December of 1972. Apollo 13, of course, was one that was planned to land and did not, damaged by an explosion, but rescued primarily by the hard work of the 20-year-olds in mission control in April of 1970. The last 3 Apollo missions each explored different areas of the moon for 3 full days versus the 1 to 2 half days that we had for previous missions before Apollo 15. The total of 850 pounds of moon rocks and soil were brought back to Earth, and the studies of these samples, as Jim has indicated, continue actively to this day. It really is the gift that keeps on giving, as so many have said. There is great new understanding from our look at the results of the Apollo missions, and new understanding in the Earth's early history, and indeed, of course, an understanding of the history of the moon, which is one of the end members of the terrestrial planetary system and has taught us a great deal about what to expect about Mars as well. And so with that summary, let's get into what really happened during Apollo. I'll do this fairly quickly. Apollo 7, as I already mentioned, was the precursor mission following the tragic fire that of Apollo 1, what we sometimes internally call the 204 fire, that killed Gus Grissom and his crew. One thing that Von Braun used to say, and has said repeatedly, I've learned to use the word impossible with the greatest caution. And that certainly applied to what the group at the Marshall Space Flight Center and their contracting teams did in developing the Saturn V. Just as a reference to what had happened out here in New Mexico with Robert Goddard, when you look at the scale of activity that changed over time with the first liquid fuel experiments that Goddard did, and then what we actually did with Apollo, the pickup in the lower right-hand corner of your screen is roughly the same size as his launch transporter. Well, really, we can go back a little bit farther, and technology really has no clear beginning for the human race, but aerodynamics and aeronautical technology really began for us in December of 1903 with the flight of the Wright brothers' first powered flight at Kitty Hawk. And only a few decades later, John Kennedy was in front of the United States Congress challenging the generation present at that time to go to the moon and return safely to Earth. And that was just in May 1961. Hard to believe how rapidly things moved in the period between the Wright brothers' flight and May of 1961. And indeed, in 1969, Neil Armstrong, Buzz Aldrin, and Mike Collins left for the moon. Now, this picture I enjoy because it looks like everybody's very serious. This is the crew of Apollo 11 with Ken Mattingly and yours truly present. Mike Collins on the left, Neil Armstrong, of course, and Buzz Aldrin standing behind him. Now, we're all looking very sober and serious at this point because we were waiting for the acquisition of signal from Apollo 8 as they came back around the moon and were headed home. And that was December 25th, Christmas Day of 1968. Now, the Apollo 17 mission, which closed out the Apollo series of lunar landings, began in many different places, but one place was the rollout of our Saturn V launch vehicle that you see here from the Vehicle Assembly Building at the Kennedy Space Center. If you want an idea of scale, just look in the lower right corner of the building and you'll see a very large fire truck. At the time that this building was constructed by the Army Corps of Engineers, Rocco Petrone, of course, was very active in that activity. The building was the largest enclosed space on Earth. Since I understand that has been superseded by the Mall of America in Minnesota, and more recently, I think, by a 787 manufacturing plant in South Carolina. Apollo 17 launched at night. It was, I understand from what people tell me, a spectacular launch to watch. And if you look carefully in the basically the center of the picture, there are some bright spots next to the Saturn V. Those are large chunks of ice that are coming off the vehicle. Some of you will recall that we stayed on the launch pad for 2 hours and 40 minutes after going into a hold at 30 seconds due to a misunderstanding between the launch control computer and the rocket itself. The rocket was perfectly ready to go. The computer just didn't know it. It had thought it had sent a signal, discovered it had not. pressurize one of the LOX tanks in the Saturn V, and so it stopped the launch. It took about 2 hours and 40 minutes to not to solve that problem, but to convince management, of course, that you had solved the problem. The two spacecraft we used, the spacecraft America in the upper right, command and service module, was somewhat different than those that were on earlier missions, different primarily because of the inclusion of a scientific equipment bay of cameras and other sensors that Ron Evans operated while he was in orbit on the surface, and Gene Cernan and I were on the surface. The lunar module, in the lower right, the Challenger was at this time, at time of launch, encapsulated in the SWA portion of the upper stage, the S4B stage of the Saturn V. At about 34,000 miles away, I finally had enough time. This was post-translunar injection. It was all of a sudden somewhat more relaxed, and I could take the camera out and start getting some good pictures of the Earth. These pictures were designed to illustrate my running commentary about changing weather patterns in the Southern Hemisphere, some of which you can see here. I'm pleased to say that NASA has told me, and I presume this is still true, that this picture is the most requested photograph from the NASA archives. Now, our destination for Apollo 17, this is a picture that I took on the way back home, but was in the ring of mountains surrounding the Serenitatis Basin. Serenitatis is about 740 kilometer diameter basin. We had the team, including Jim and many others that were looking at landing sites, had always been interested in this Taurus Littrow Valley, but until we had figured out a change in our navigational procedures, it was off the table just because of the difficulty in landing in a valley that was only about 7 kilometers wide at its narrowest point. Now, relative to the Apollo 11 mission, this is approximately the distance. We were some 600 kilometers north and quite a significant amount east of the Apollo 11 landing site. Taurus Littrow, this picture taken the orbit before we descended into the valley itself. Taurus Littrow was a valley, as I indicated, about 7 kilometers wide at the narrowest point, about 50 kilometers long, and it was a Grauman-bounded valley, as we now know, and had suspected, of course, even before the mission, that had been formed as part of the dynamics of the formation of the Serenitatis Basin. Now, Serenitatis, there's still some controversy of whether it was one large impact or two, but nevertheless, I think it's generally accepted that this valley was created in the ring of mountains due to extensional forces in the ring of mountains that surround the Serenitatis Basin. The object some of you, I hope, can see that's right in the, more or less in the center of the picture, a little bit down and to the right of the center fiducial mark, is the Command Module America. Ron Evans at this point was taking some final landmark sighting measurements using the sextant that he had on board that in turn were sent back to Earth, recalculated in terms of his state vector, and then that information was put into the Lunar Module Challenger state vector so that we had a much more precise understanding of our position relative to the planned landing site. Without that procedure taking place on the orbit prior to landing, and getting that information loaded into our guidance system just before we went into powered descent, we could not have landed in this valley under the then existing mission rules. The error ellipse would have just been too large. But that was worked out between the mission control folks in Houston and the Belcom people that Jim worked for at the time, and really enabled us to go into a really remarkable geologic environment. I throw in this LRO picture just to illustrate more of what we landed, but it's sort of a spectacular low oblique that LRO has taken, the Lunar Reconnaissance Orbiter, of the South Massif. That massif, by the way, is about 2,100 meters high, and we had known before the mission that an avalanche had come off the side of that mountain. It was almost certain that it was an avalanche, probably fluidized avalanche. And this picture, though, illustrates the scar. All the time we were on the surface, and in any previous pictures, we had never really been able to say, yeah, that's a scar. But this one pretty well says that's a scar. Now, up in the upper part of the mountain, Mark Robinson and some of us are arguing over whether we have a deposit of melt breccia that might have come from Tycho and triggered the avalanche. On the other hand, as you can see in the, I don't know whether my marker shows on the screen or not. We didn't discuss that. But to the, towards the foreground, from the edge of that avalanche, you can see there's a darker covered material, also looks like an avalanche. And so there's a lot of evidence I won't go into, but you can read in our recent paper in Icarus, a lot of evidence that indicates that we now have to assume that there were two avalanches over time, and that may mean that these avalanches are being triggered by seismic activity related to the Lee-Lincoln Fault, that you can see signs up there, rather than by ejecta from Tycho. But the timing may have been pretty much about the same. The Challenger, though, landed, as you can now see, with that light-colored spot that is there. It's real. It's caused almost certainly by the winnowing of the darker fine regolith material, the agglutinates primarily, away from the descent engine effluents. So in this particular picture, you get a really good idea about where we actually landed. The crater just above the white spot where the Challenger landed is the crater Camelot that we will probably talk about more in a little while. This picture from Apollo 15 is the really the basis for essentially all of our mission planning. We had some orbiter shots, lunar orbiter shots, as well as some other Apollo 15 photographs. But our identifying resolution for planning was probably something on the order of 15 meters. Certainly the LRO now is providing far better photography of that. And indeed, Ron Evans' photographs that I showed you earlier gave us much better resolution too. But one of the things that in the, by the way, does my cursor show on the screen?
No, it doesn't, but there's a arrow icon at the top. If you click on that, a green arrow will show on the screen, and you can click it and drag it around the screen.
An arrow. Well, I don't see that. That's okay. In the upper right, you'll see some linear dark features across what we call the sculptured hills. Turns out we now have, through LRO, good evidence, I think, that those are volcanic pyroclastic fissures. And that's just to show that we had that information maybe earlier, but did not fully recognize it. Again, that's the landing point. This LRO picture, which many of you have seen, I hope, just shows the Apollo 17 landing site, again, around the lunar module descent stage that is still there. You see that light-colored area that was the spot in a previous image. This picture also helps to illustrate just how good LRO is, in that it not only shows the disturbed area of my footprints headed out towards the Alcep site on the left, but it also, you can see the tracks of the rover, the dual tracks of the rover. So really fantastic image quality coming from LRO. Certainly something we ought to continue to use as long as we can and target for some very important new information. The rover is parked, it's that dark spot at the lower right edge of this image. First view I had, however, out of the right-hand window of the lunar module was this one, looking at the base of the North Massif. That base in the center of the picture is probably about 5 kilometers away. The very typical looking regolith, except in this case, and in all cases of landing, there's been that winnowing effect so that you have less of the dark material immediately around the landed module. The boulder that is in the near the, about an inch, well, whatever, in my picture, about an inch away from the left edge, upper left edge, that's geophone rock. That is, and so that's the area near which the Alcep was eventually deployed. The bright metallic object in the foreground is one of 16 thrusters that we use to control the attitude of our spacecraft as we flew in space. It had about 50 pounds thrust, obviously was restartable. And just for comparison, the one of the F1 engines in the first stage of the Saturn V had 1.5 million pounds of thrust. So we did a lot with different propulsion technologies in order to accomplish the Apollo mission. What you need to have on the moon in order to survive at least for 3 days, and ultimately, conceptually, you need the same kind of thing, is obviously a place to live, which was the ascent stage of the lunar module. You need transportation to get around, which in our case was a lunar rover. And you need another spacecraft, which contained the human being that you see there in the foreground. It truly was a spacecraft. It had a life of 8 to 9 hours, depending on how you used it. It worked very well. The A7LB suit worked very well for the Apollo program. I hope we can do much, much better in the future. But it did the job that we needed to have done. It had life support. It had water-cooled underwear in order to stay cool. We couldn't have operated without that. That was as much an enabling technology as the Saturn V. And of course, one thing it didn't have was food, other than a fruit bar that we could reach down and grab with our teeth and get a little bit of nourishment for the 7, 8, 8.5 hours that we actually were in the suit pressurized. And it always helps to have the support of the American taxpayer in order to make these kind of things happen, which is represented, of course, by the American flag. Those flags, I should have pointed out, are still, at least their shadows are still visible in those high-resolution Apollo or LRO photographs that we saw earlier. Now, just 3 different areas of some of the science, specific lunar science that we obtained in this rate sample from the Station 1 out near Steno Crater. We obtained a large number of basalt fragments that gave from obviously different parts of a basalt flow, and through their analysis, we can now get a general picture of the process of crystallization of these flows. And one of the surprising things, to me anyway, that comes out of that analysis is that plagioclase is a very early crystallizing phase and almost certainly floats in the highly fluid magma, low density relatively high-density magma, and causes differentiation, along with olivine forming pretty much at the same time and sinking. So you have a fairly rapid differentiation process going on in these highly fluid, titanium-rich flows. As the Icarus team and I have written about recently in the paper published last year, we also, I think, now have, I think, a much better understanding of basin stratigraphy, at least for Chrysium, Serenitatis, and Imbrium, and the age sequence in that order. By looking at the various breccias, melt breccias that have rolled down the mountain and leaving boulder tracks, so we can tell actually where they came from. This large boulder was visible on the pre-mission photography, and so became Station 6 in our third EVA. We did not, Station 7 was sort of an ad hoc station. We were going to try to find another large boulder, and we did, and we sampled it, but we did not know that it also had a boulder track until we saw the LRO photography of this area. And so we did get some significant stratigraphy, separation of about 500 vertical meters from the mission, which we didn't fully realize until we had the LRO photography. This slope doesn't look like it in this picture because of the camera orientation, but the rover and yours truly there on the left are working along a 20-degree slope in the talus material that's developed at the base of the mountain. The boulder broke in two when it hit that 20-degree slope because it had been rolling down about a 26-degree slope. Rolling, I'd say bouncing was more like it when you really study the nature of those boulder tracks. There again is the lunar rover the lunar module location, the Challenger, and you can just barely see maybe the light-colored area that's caused by the descent effluence. Well, I'm going to show you this picture. Ron Wells, a colleague of mine, who's doing great things with his son in color balancing the Apollo extrachrome film images. This is the trench that I dug at Shorty Crater that exposed what we found out subsequently were pyroclastic ash deposits. There's an awful lot that can be said about this, and I'm writing up some of that right now. I've mentioned it a few times, as Jim knows, at the LPSC meetings, and more is coming out of the analysis of the few samples that we were able to collect. We only had 30 minutes to work at this site because of constraints on backpack, oxygen, battery, and water supplies. But nevertheless, I think we really did get a terribly valuable trove of information from these pyroclastic ashes. Not only from the ashes themselves, which contain some indigenous water, as we now know from Jim's colleagues, but also contain volatiles that just almost certainly have to come from deep within the moon. We may be able to talk about that a little bit more later. Now, I'd like to just give you, hopefully, a quick review of what the Taurus littoral sample data is that relate to the nature of the lunar crust, upper mantle, lower mantle, and core. And we'll just go in reverse order there. From the core, we now are getting increasingly amounts of paleomagnetic data. For example, the light gray soils on either side of these pyroclastic deposits turn out to have extremely low maturity, even though they had to be deposited about 3.5 billion years ago. And that suggests very strongly that the global magnetic field was active at about 3.48, 3.5 billion years. That's a little bit later than had previously been estimated by the Weiss team at MIT, and those are the numbers that they come up with in microtesla between 4.25 and 3.56 GA. Now from samples at Station 5, which we now, I believe, is fairly clear we can reorient to the horizontal and get paleomagnetic field orientations. One has been published so far, 75055, and gives us a magnetic field orientation that is roughly consistent with the existing axis orientation of the moon. Well, for some reason, there we go. Okay. The upper lower mantle now, that's at depths greater than 500 kilometers. We almost certainly are getting information from the pyroclastic ash about the volatile content of those of that portion of the moon, primarily because those volatiles do not resemble in any significant way the volatile, the very low volatile content of the Mare basalts, which appear to have formed from magmas generated in the upper mantle. My hypothesis is that indicates the upper lower mantle, at least, if not the lower mantle in general, is chondritic in composition. Did not participate in the magma ocean. Otherwise, those volatiles would have been lost. And Clive Neal and his team have done work some time ago that indicates garnet, trace element work, that garnet was on the liquidus of the magma that was generated. Now, that magma almost certainly was generated in the lower upper mantle and probably stimulated in part by the movement of volatiles from the upper lower mantle. The deep upper mantle, we now have, I think, a sample, 72415, of the olivine dominant cumulate in the very deep upper mantle, and somewhat slightly higher, the trochlite 76535, that indicate that there has been overturn of beneath the Procolarum basin, at least. I have to admit, I was always a skeptic of the overturn hypothesis until I began to study this 72415 sample, as well as the trochlite. And there is evidence in those, evidence from Wang, that light iron isotopes are enriched in the dunite, which was always a bit of a problem, since almost all other isotopic systems are consistent with the isotope ratios of the Earth. Now it looks like we know where the light iron went. And then I started to look at the work that Chip Shearer and his team did on the coronas within the trochlite 76535, and noted these coronas could well be after chromium garnet, and they are very specific relative to their position on the sides of olivine crystals and plagioclase crystals, with chrome spinel clinopyroxene on plagioclase and chrome spinel orthopyroxene on olivine. This is the type of coronas that I observed when I worked on eclogites in Norway, eclogites that had, and dunites that had been moved fairly rapidly from high pressure to low pressure, and these kind of symplectic coronas develop because of that fairly rapid movement, change in pressure. So we'll see, but I think we're beginning to know how to sample, how to look for samples of the lower mantle, upper mantle. Now, the upper mantle residual is certainly thought, and I think correctly, is the residual magma ocean. The question is, how do we get the creep signature into the magnesium suite of samples? We have two very nice norites from the Apollo 17 collection. Again, I think it relates to this Procolarum basin forming event at about 4.35 GA, which is the age of a large portion of the MG suite samples that have been brought back from all landing sites. If you form a basin the size of Procolarum, now some 3,200 kilometers in diameter, you would expect to have a major drop in lithostatic pressure at the instant of impact, or just after impact. The residual magma ocean that would have been in place beneath the crust may have migrated to that low pressure region of Procolarum, and thus given us the creep terrain that has been identified primarily through the ejecta from the Imbrium basin. Procolarum probably did not bring that material to the surface, but Imbrium did. The MG suite upper mantle may have originated from the orthopyroxene-rich zone developed in the crystallizing magma ocean. Again, the norites give us some information about that, as well as what appears to be a pluton, a large pluton forming the sculptured hills that was ejected from Imbrium. The sculptured hills do look like the equivalent of the Frau Maro formation, and are the last major ejecta to reach the Taurus littoral area. And the M-cubed work, Carly Peters and others, has certainly given us more information about the composition of the sculptured hills than we ever could have gotten from the samples themselves. For a long time, we didn't think we had sampled at what was Station 8 at the base of the sculptured hills. We didn't think we had sampled the sculptured hills. We just sampled a boulder, a norite boulder, that was sitting out on the surface. But now I'm almost convinced that norite boulder is one of the rock types that makes up the sculptured hills. And there may be others that we have in the collection that appear at Station 9. It looks like to me that the Van Sert crater impact actually hit into sculptured hills material that was only very thinly buried by basaltic magma. We've talked about the importance of this Procolarum basin forming impact, partial melting of the OPX rich area within the upper mantle. MG suite magma is assimilated and mixed with your creep as they moved upward into the lower crust. And then the Imbrium was the primary excavation impact that brought them to where we actually were able to get some samples. Now, Apollo 15 creep basalts may have originated by the same assimilation process, but actually some of those creep basalts may have reached the surface soon after the Procolarum event. That's something to be worked on later. Upper mantle volatiles and crustal lithostatic material. We had a unique opportunity, at least within the Apollo program, of examining old regolith on the North Massif versus young regolith on the South Massif. That young regolith developed after the avalanche had taken place about 100 million years ago, and had cleaned off the South Massif the older regolith on the South Massif. And when you do that, you find that the old regolith is dominated by mineral fragments, primarily pyroxenes and plagioclase, and the young regolith is dominated by breccia fragments, melt breccia fragments, a very distinct particle type frequency distinction. Turns out there's also a particle size frequency distribution distinction as well. I always felt for many decades that something must have happened before the Mare basalts in any given region erupted at the surface, because we know that there are some volatiles in the Mare basalts. Not a lot, but there's some. Otherwise, they wouldn't be as vesicular as they are. And so when I had this opportunity to look at old versus young regolith, it occurred to me that maybe we could get some insights into what happened before Mare eruptions. And I think it was the very early evolution of volatiles before melting in the upper mantle that provided the impetus for pyroclastic, or I would call them lithoclastic eruptions preceding Mare basalts. And at Taurus Littrow, of course, we had the two massifs and an opportunity to examine what that old regolith might look like. Now, I would suggest that we go back and re-examine the Apollo 16 cores because they may well indicate what Cayley formation is like, and that some of the Cayley, I think there are different Cayleys, but some of the Cayley are pyroclastic deposits related to this pre-Mare volcanic activity. On the far side, as I flew over some of the very large basins there that have extremely smooth floors, I could see also that there are rimless Mare-like craters in some of these basins, which may be the eruptive centers for this pre-Mare pyroclastic material, at least in that area. Now, it's going to take some re-examination of, I think, LRO material in order to see if we can identify such craters on the near side that might be the source of lithostatic pyroclastic eruptions. Okay, the upper mantle, very high titanium Mare sources are probably just below the original lunar crust. They are the dominant basalts at stations around the limb and at 1 and 5 in Taurus Littrow. The reason I think they're fairly shallow and early in the Mare sequence is that that's where the ilmenite is. As a cumulate, the ilmenite was late in forming in the magma ocean, and would therefore be needed in order to develop these very high titanium Mare basalt sources. Also, many years ago, I did some work on rare earth elements, and I think that there's a distinct story to be told there. Somebody might want to work on that also indicate that partial melting that produced the Mare basalts started high and moved downward over time. And in that context, you have to consider that the moon would not have remelted if we hadn't put the insulating mega breccia layer on top, as well as having a concentration of urcrete heat sources below that insulating layer. Just might note here that we do have high titanium basalts indicated by remote sensing in the Procalarum region. And that they may have resulted because of this overturn that we talked about earlier, with your heat sources moving downward, and then therefore producing partial melting of basalts that then erupted in the much later in the focal arum region. Upper mantle medium titanium and very low titanium basalt sources would be below the high titanium sources, and we have rare fragments of these at stations 1, 4, 8, and in the deep drill core. Most Taurus littoral conduits, though, were probably sealed off by the very high titanium basalts, their eruption, so we don't see much of that at Taurus littoral, but there are some indications of that, and Noah Petro has been working on whether or not we might have some low titanium pyroclastics developed in some of the fissures, particularly the fissure that we've identified on the North Massif. There are also low titanium glasses in the deep core, in the bottom of near the bottom units of the deep core, as well as in the Station 8 rake sample regolith. And with those fissures that we've identified in the sculptured hills, some of them may be quite late and producing and have produced very low titanium to very low titanium pyroclastic glasses. That is still something that is in work in my mind, and hopefully we'll get something out on that by the time of the LPSC this year. The upper lower mantle, that is above 500 kilometers, and the lower upper mantle, we've already talked about a bit, probably the source area for the pyroclastic ash, the orange ash, and also probably for the colorless low titanium glasses that I just mentioned. Pressure release melting may be the primary way in which these pyroclastic magmas develop, and I would guess maybe the graben faulting around the big basins is reaching very deep into the moon and providing that pressure release. But sometime after at least the Taurus littoral, after 3.74 GA, which is the sort of the average age of the Mare basalt data that we have on ages. That's an area, by the way, that I think really needs to be worked on, is trying to get some kind of rational age date on the Mare basalts in Taurus littoral. They're just, the age dates are all over the map, and no matter what isotopic system you use. So we have a lot of work to do there still. And of course, those pyroclastic eruptions were driven by volatiles from the chondritic lower mantle. I mentioned the fissures that we've seen in the sculptured hills. There's one on the North Massif. Almost certainly there were fissures in the valley floor. I can't believe that all of the fractures were filled with Mare basalt. They might have been, and because of the work that Jim and others have done on the very broad distribution of pyroclastics from eruptions on the moon, it may be enough that the fissures on the massifs were sufficient to cover the valley with pyroclastic ashes. There's no question that almost the entire valley and many other parts of that portion of the moon have been covered by pyroclastics. Not very thick, maybe a meter, most 2 meters, but nevertheless, that at one time, about at least for Taurus littoral, at about 3.5 billion years ago, the entire valley and the massifs were almost certainly covered by this layer of pyroclastic ash. Now, with continued detailed synthesis and going to other landing areas, we'll continue, hopefully, to flesh out our understanding of the lunar interior, its evolution over time, and maybe even the origin of the moon itself. Even though there seems to be a consensus about the giant impact hypothesis, I've been a skeptic for many decades. I think it's just too complicated, and I've always been skeptical of complicated model-dependent hypotheses. But yeah, there is evidence, I think, of an independent accretion and capture. We have identical or nearly identical isotopic ratios with the Earth, evidence of a deep magma ocean below 500. That should be above 500 kilometers, and devolatilization of the upper mantle of Mare sources, namely the upper mantle, probably by continued accretionary impacts, and evidence of a chondritic lower mantle, as I've talked about before. And the volatile sources, of course, are below the upper mantle. So after 46 years, maybe someone is getting serious. And having participated in one of the sightings of the directives now being issued by the White House, directives to the Space Council as well as to NASA, one can only hope. However, I do not see in NASA yet a full understanding of the geopolitical urgency for getting the United States back into deep space, and particularly to the surface of the moon. There is certainly not an Apollo environment of managerial activity. NASA is not young like Apollo was. It must get there and stay young. And somehow the Congress and the White House have to agree that if you're going to establish milestones, you also establish management reserves so you can make those milestones. Missing milestones is the political death knell of any major scientific activity. And critical path planning really needs to get to work, get going right now and in a hurry. And Jim, I think I'll stop there and see what kind of questions we have. I know I have a lot of other stuff on the site, but we can maybe get into some of those issues with questions.
Okay, that's great, and thank you very much, Jack, and for all of you listening in. As they say, it's obvious why I mentioned earlier, if you have any questions about why it's important to send humans and scientists as well to the moon, not that they're not equivalent, of course. Jack just demonstrated that in space. So we have some questions, and I think Ashley Palumbo will synthesize those and mention a few of them to you. And I would like to go back to save some time for the rest of your talk, too, because I think it's really critical for the future. Okay, Ashley?
Great. Thank you, Jack, for sharing this very interesting presentation with us. We have a lot of questions for you, so hopefully we can get through a good number of them.
I'll try to be brief.
Okay. The first few questions focus on your time on the moon. So first, what are the key differences between the geologic training that you received before the mission and the real lunar surface? In other words, did the training experience help a lot in exploring the moon, or did you find it to be very different?
Well, the moon, yes, I found it to be very different. But that isn't because, but I also expected it to be very different. We had a lot of information about the surface of the moon by the time I flew. And in fact, from Surveyor onward, we had a fairly good idea of the kind of geological environment we would be dealing with on the moon. And that's one reason why when I persuaded Al Shepard and Jim Lovell to establish a simulation-based training program that Jim alluded to earlier, that was based on that understanding that we would never have good analogies here on Earth for training, but we would have some analogies. that we could take the crews to for about a week a month and immerse them in the geology, new geology that was relevant to their mission, but also which made them very, very familiar with the equipment, the documentation procedures, the cameras, and everything else that they would have to put with. So that those would not be distractions, unnecessary distractions once they were on the moon. Let me just give you one example. The regolith is indeed regolith. It's a mixture of fine and coarse-grained material, and there are places on Earth, such as alluvial fans, where you get that kind of a mixture. And it was not an accident that the only major or significant training exercise we were able to get for Neil Armstrong and Buzz Aldrin was on an alluvial fan deposit near El Paso, Texas, the Guadalupe Mountains. So yes, we tried to do that as rationally as we could, given that the Earth and the Moon have had such remarkably different geologic histories.
Great. Our next question is, you are one of the last people to have walked on the moon. How does that feel, and in what ways do you hope to be involved in the training of the next generation of lunar explorers?
Well, I feel very honored and privileged to have ever even participated in the beginnings of Apollo, much less to actually have had the opportunity to fly on Apollo 17. That was both a geological and a national contribution that I hope that I have lived up to. My current involvement is I would have to say sporadic, in that I am a member of the user advisory group to the National Space Council, and as such are trying to make some inputs along the lines that I dealt with just a few moments ago, in that there needs to be a sense of urgency to get back to the surface of the moon from a geopolitical perspective, and also to realize that it is on the surface of the moon we're going to learn how to really explore Mars. Mars is not going to be easy. Getting there is not going to be easy. Landing there is not going to be easy, and sustaining yourself on Mars is not going to be easy. So the moon, only 3 days away, is the place to learn, to try to develop the technologies as well as the understanding necessary to solve the problems that face us, daunting problems that face us in getting to Mars, and to actually working there. Now, one of the big aspects of that, of course, is our lunar resources. And they can play a tremendously important role, not only in future settlement of the moon, but also in the providing the necessary consumables for dealing with Mars transit and Mars exploration.
So just to add to that, that Jack has also been very active in with each of the new astronaut classes. So we have sort of a planetary science week, and Jack has come to virtually all of those and really brought the new astronaut classes, sharing his vision of essentially destinations and his time on the moon. Ashley?
Great, thank you. Our next couple of questions focus on differences between the Apollo era and the current era of exploration. So first, you spoke about the differences in lunar data quality between now and the time of the Apollo missions, as well as the large amount of information that you and the other Apollo astronauts learned while on the surface. Looking back, what do you know now that you wish you knew when you first got to the moon?
Oh, I tell you, I wish I had the LRO photography, and as well as the M-Cube data. Those two things would have, I think, altered portions of our plans. Although I've looked at our plans, and it turns out they were pretty good based on the photograph we had. It's hard to say you would done anything differently, except now with this data, I think we would have made a bigger push into the sculptured hills. That information now that we have now about the sculptured hills, really I think would change how Jim and I and others would have looked at the plans. But otherwise, gosh, how can you argue with the kinds of things that came out of the stations that we picked, and all of which we wish we had had more time to spend there.
See, Jack, we should have gone for Bird Crater. You know the one.
Yeah, well, that might have been a little bit far, but we might have changed our landing site too.
Yep, true.
No, Jim, that kind of speculation probably is not very fruitful. What you needed were a couple more days.
Absolutely.
Great. We've been in this class thinking a lot about the role of robotic exploration of the moon, and specifically we're wondering if you think there will ever come a day when robotic exploration is so effective and so advanced that human exploration becomes somewhat unnecessary, or will there always be a role to have boots on the ground?
Well, as far as I can think ahead, I think human exploration is going to be essential. Particularly when you have trained and experienced people conducting that exploration, it becomes much more efficient. Now, that's not to say that robots don't have a role. I see robots in a precursor role, as Surveyor was for Apollo, and I see them as a post-cursor rule, if I may coin a term, where you learn something, as we now have learned, from the analysis of samples and observations and photography, and you would like to send a robot back to expand on what you've learned. I have been, and I guess I still am, a skeptic of whether a robotic field assistant would be very efficient way to deal with things. I think having advanced, sophisticated, rapid analytical equipment would be very, very useful. But I'm not sure you want to have a robot that you either have to direct or have to pay attention to, cutting into the efficiency of your actual field excursions.
So you just mentioned the idea of having astronauts that are very well trained for their exploration, and that leads us into another question from someone in the group. And they want to know, when you're thinking about future human spaceflight and lunar exploration, what do you see as the role of astronauts that are more scientifically oriented versus astronauts that come from a background of being a pilot, for example? And how do you think this future of exploration could compare to the Apollo program?
Well, I think future exploration will expand on Apollo 17, where you have both the expertise, technical and piloting expertise of experienced professional pilots, and you have the scientific expertise of experienced and professional scientists. I don't see anything incompatible with those two. Now, as crews get larger, and I hope they do, then you probably will continue with that mix. Part of the mix depends on how willing you are to, or we would be, or the implementing agency would be, to depend on non-piloted landings, automated landings. That's going to be an interesting discussion to have in the long term, particularly when it comes to Mars, because with the communication delays, mission control is not going to be involved in an actual landing on Mars. They aren't today, and they won't be in the future. It's just too far away. And that leads me, for example, for Mars, to do something new philosophically, and that is, don't plan to abort to come home. Plan to abort to land, and then work on any problem that you might have caused that so-called abort. And those kind of things are the kind of things we can work with and learn from by simulating on the moon.
Jack, this brings me to another point here. You point out the role of, different types of people in making mission success. One of the key, really important aspects of Apollo was the teamwork, the team of the astronauts, the teams of the science and engineering synergism, mission control, et cetera. You've already mentioned the critical role that Ron Evans, the command module pilot, played in validating the landing site. Can you talk about the team as a whole, a little bit about Gene?
Well, I think that in every mission, pretty much, the teams gel fairly quickly and work together very well as professionals. That's just what you expect to happen. And that's one reason, Jim and others, that I still recommend to NASA that whatever your professional discipline might have been, pilot training is an extremely important part of developing a team attitude in that it gives everybody sort of a baseline technical and professional background that on which the team can build. NASA has not listened to me, but although now the new crews are getting more and more fun piloting time, and are actually, I think, going to be checked out as pilots in the future. But that going to T-38 training with the Air Force and helicopter training with the Navy, I think really made a big difference in how these teams came together.
Excellent. So, Jack, we're going to have two more questions, and we really would like you to run through the rest of your presentation about the future, and too, if we could do that. So
sure.
Back to the.
One of our class members was wondering what advice you have for future astronauts that will be going to the moon, or people who might want to be a future astronaut that will go to the moon. Specifically, what advice would you give for someone who would be spending a long duration on the moon or potentially a trip to Mars?
That's everybody in the class, by the way.
I hope so. The first thing is that for those that are still, you never stop learning, and never stop learning. Build as broad a background in relevant fields as you possibly can. And again, I would say always get a pilot's license and go as far as you can. I think I just can't emphasize enough the amount of confidence and skill that piloting gives you. And I think it's very, very important, and it may well be important in actually getting selected to show that you've had that initiative. As far as physical preparation, if that's part of the question, you just have to get in great shape, stay in shape. And for those of people who are going to work in a pressure suit, anything like the A7LB, you need to have specialized trainers to help you work the muscles that are important to being able to be efficient, to use your hands. We take human beings into space, whatever their professional backgrounds are, and we use their brains, their experience, their eyes, but we have never fully utilized their hands. We came close with the construction of the International Space Station, but there again, it emphasized my point. Specialized trainers were used in order to develop those forearm muscles, the endurance as well as the strength, in order to have long EDAs in that construction process. We did not understand that for Apollo. And so our forearm muscles and hands were continuously tired and fatigued. Fortunately, in 1/6 gravity, that goes away in one night's rest. You have no residual soreness, but it still interferes with the efficiency of the EVA itself. So physical conditioning is extremely important and can't be underestimated. Now for Mars, as we are learning from the International Space Station experience, shuttle experience, Skylab in particular, we still have a lot to learn about how to maintain that physical strength and the basic physiology of the human body, so when you get to Mars, you can perform as well as you would like to perform. We really have wasted a lot of time in learning what the scientific foundations are of space adaptation, the scientific foundation of countermeasures to its adverse consequences. And I would hope that as long as the space station is viable, that we sort of reorganize that effort and with an emphasis on learning everything we possibly can learn that human beings are going to experience physiologically on an exceptionally long trip to Mars. And of course, I think helium-3 fusion rockets can shorten that trip, but that's a different subject entirely.
Okay, one more question and we'll go to the rest of your presentation.
For our final question to wrap up, we wanted to talk a little bit about terrestrial analog missions for space exploration, which is something that some members of our class have taken part in. So our specific questions are, what new insight can these advanced and long-term terrestrial analog missions bring that you may not have had before Apollo? And similarly, as an astronaut, how do you feel that this sort of analog work can be improved to better represent actual human exploration?
Boy, I tell you, I think people in your class that have experienced these long-term analog missions are probably better able to answer that question than I am. Our analog missions were basically the training exercises in the field, and although we did some early testing, Joe Kerwin and Jim Irwin and others, excuse me, did some early testing in the spacecraft, just surviving in the spacecraft for several days. That's not what we're talking about. We're talking about very long-term activity. I tend to have great confidence that human beings are going to adapt to whatever situation you put them into, and that there may be some issues that are identified in long-term Earth-based 1G analog missions that can help in the planning of long-term transit as well as long-term stays on the Moon and Mars. But I have great confidence that the people that do those things are going to adapt very rapidly, and you'll find that not a lot of that analog planning is relevant to the real situation.
Thanks, Jack. One of our students here, Laura Lark, she spent 8 months in the high seas habitat on Mauna Kea, so we'll turn to her for more information too.
Yeah, I'd let. She ought to present her experience, and I'll listen to that because I really don't. I'm really up in the air on this whole business of analogs.
Okay, we'll arrange that actually. Okay, so Jack, if you can press on with your presentation and take us into the future, it'd be great.
Okay, well, I'll try to go very quickly. You've probably gotten some of my feelings already. We need to really understand the critical geopolitical nature of space dominance for the indefinite future. This is literally the new ocean. It's as important as the oceans were to previous generations, and it's only going to get more important as time goes on. And I think the protection of liberty calls us to its defense in space as well as at home. That's a very strong feeling that I have, and the United States has to at least be the leader in that effort. Now, focus is required if you're really and truly planning to get back into deep space and do it well, manage the risks that are there and they haven't gone away, then you have to focus. And right now, I don't think we have an agency that is focused on doing that. NASA has many distractions from that primary mission that occupy the time and productivity of management and the implementers. as some of you are probably aware, I think that NASA either needs to be reorganized along the lines of Apollo with a couple additions, or it needs to, we need to have an agency that's particularly chartered and challenged with the job of getting us back into deep space. The important to that is having adequate reserves. We mentioned that a little bit earlier. It's the only way you have, monetary reserves are the only way that you have in dealing with the unknown unknowns, unless you slip milestones. And we've seen many programs run into problems by slipping milestones in order to fund the things you didn't know you were going to have to fund. We nearly did not ever launch the space shuttle because of this, and the cancellation of Constellation illustrates that as well. Had the funding reserves been there for Constellation, the momentum, I think, would have been too great to allow its cancellation. Apollo reserves were about 100%. It's an interesting story about how that happened. Jim Webb, the second administrator of NASA, asked people like George Lowe and Chris Kraft and Bob Gilruth and others in his engineering group to independently estimate what it was going to take to accomplish Kennedy's challenge of putting a man on the moon and returning him safely to Earth. And they came back with around $8 billion in those year dollars. And so Webb, when he went to Congress and the OMB, he said it's going to cost 16. And they believed him. And that's how we got the 100%. And we used it all. Believe me, we used it all. But what those reserves actually did for us, you might not need to do this quite as much now because of the advance of technology, but it enabled us to have critical systems on critical objectives on parallel systems tracks. Such as, I'll give one example, and that's the engine that powered the ascent stage of the lunar module Eagle. That was not doing well in tests. And actually, it was one of the reasons why we flew Apollo 8 was the lunar module was having problems getting through tests. And it was about 6 months behind. That engine was replaced by another engine that was under development. And that second engine was moved forward. And that's the engine that Neil actually used to get off the moon. So that's reserves enable you to do that. Enables you to make milestones, stay on schedule. So it's now today, I would say 30% might be what you need to have through critical design reviews. We're technically smarter than we were in the 1960s. Unfortunately, we do not have the same management environment that we had in the 1960s. Stable annual funding is a no-brainer, and that can only come if we establish the concept of an indefinite commitment to the geopolitical competitiveness of the United States in space. Unless you have that commitment, like you do with the to be competitive in other national security areas, then it's going to be very difficult to take on a return to the moon, settle the moon, and on to Mars effort. It has to be an indefinite commitment, and that this is important to the future of the country and its ideals, as is the military. And there are a lot of lessons to be learned, I think, from the military, particularly on how to stay young, and we'll talk about that in a moment. The average age of Apollo engineers, for the most part, were in their 20s. Gene Kranz did that calculation during Apollo 13 crisis, and in the Mission Control Center, the average age was 26. We tend to forget that. And that great things are done by young people managed by slightly older people. And that's we've got to realize that. and get back to that and figure out a way to keep whatever agency is undertaking the national programs, how to keep them young. The military does this. One of the best examples is the nuclear Navy. Civil service rules need to be modified so that NASA or the agency doing this is going to be able to stay young. The technical currency and flexibility is certainly extremely important. We don't want to reach so far that unnecessary technical risk is assumed. However, you need to design all your major equipment for continuous upgrades in technically fluid fields. Actually, most fields are so technically fluid today that that's also a no-brainer. NASA during Apollo had a very strong internal agency engineering design strength. It was critical to managing contracts. At times it was critical actually to producing solutions to problems. But with the space shuttle era, that was lost for the most part. And NASA became very dependent on the contractor design engineering. I think it's very important for NASA to redevelop that strong engineering design strength internally, not only to manage contracts, but to provide managers with alternative solutions to problems. For example, if a problem developed in tests at JSC where I was stationed, almost immediately people would get together in NASA. NASA people would get together to try to work out what the problem was, what the options were that management would have to solve it. And literally the next morning, often, that would be in front of George Lowe. And at the same time, the contractor, say it was Grumman for the lunar module, would have been doing the same thing, and they would have their options to present to Lowe, and Lowe would at least have that kind of independent evaluation of the problem and of his options for solution, rather than just one. I think that's one source. So that's what I'm getting at here for strong in internal design strength. Now, we had a very open management environment in Apollo. There were a minimum number of levels of decision making. That has changed severely since. Apollo always allowed a good idea to rise quickly to a final decision maker. And sometimes, as I indicated, that would be overnight. Now, what you have to do, you have to build into an organization a method to avoid decision creep due to success or failure. Let me give you an example. Somebody does a really good job, they get promoted, you can't let them take their decisions with them. You have to leave those decisions at the level where that really good job was originally done. The same goes for failure. Somebody doesn't do so well, you don't move their decision making up a level. You change the problem at the level where the originally it appeared to be best to leave it. That's what I'm talking about. That happens in every agency. I saw it in just a brief time I was at NASA. Late in the game, decisions were creeping upward until when I worked at NASA headquarters, it took forever to get a decision made. Risk management. I've had a bit of a discussion at an open meeting at the user advisory group when people kept emphasizing that things had to be safe. Well, I finally erupted, unfortunately, and said, it's never going to be safe. You just have to manage the risk. And I say that again. And this management of risk has to be embedded at all levels of implementation. You identify your major risks. and you manage their mitigation as best you can. But in advance, if you're going to have problems, you prepare on how to respond to the risk and to the problem that may develop. That's what mission rules were all about in Apollo. That's what our training was all focused on, was being able to manage problems should they occur. Now, the problems we anticipated almost never, with some major exceptions, never occurred. That's all right. You're learning, you're trained, you're training yourself on how to manage risk and how to deal with risks and problems as they occur. The old adage of you train intensively as close as possible to how you would fly. That's extremely important, or how you would explore. You train as close to that as you can so that the unexpected can be dealt with. And operators, well, there we go. Operators are better able to handle the unexpected with all of this preparation. Now, by critical paths, I'm talking about critical paths to get back to the moon, for example, need to be under U.S. control. We have run into a problem in getting Orion on schedule. It's not on schedule because we farmed out the service module. And the European Space Agency has run into repeated problems in dealing with that. Though we are not in control of the critical path to get Orion back into space. That is a big mistake. But if you have strong leadership in a domestic space program that is moving forward, that has reserves, that's going to make milestones, then there are opportunities for international partners, and they can utilize those. I think that is also an Apollo model. People forget that Apollo had a great deal of international participation, particularly on the science side. And because we were providing the opportunity for international partners to utilize the Apollo systems in order to do science. And there's nothing wrong with that. I'm all for that. I think that's extremely important. One other thing that we have to deal with is how we drive diversity. You have to drive diversity without giving up on skill. Political correctness, if political correctness drives diversity, you're going to run yourself into some problems. STEM educational institutions are the farm team. I'm thinking of this as an indefinite commitment to deep space exploration. And so you have to have an indefinite commitment to education and to developing the people who are ultimately going to be the next generation to replace those that have hit their 8 to 10 year limit in productivity. What about public and private space? Private investment has long been a part of aerospace. People tend to think it hasn't been. Early entrepreneurial aircraft industry is one of the earliest examples of that. The P-51 was not designed to government specs. North Americans built it and sold it to the government. You have to remember that. And that's what's happening in the area of launch vehicles and spacecraft right now. Satellite communications. NASA kicked it off with some of the early Eisenhower-era communication satellite tests, but that took off and now is a huge industry that both government and the private sector depend upon. Contractor teams in the Army Corps of Engineers implemented most of Apollo. NASA was the guiding light, but it was implemented by these teams. But the technical and managerial strong oversight was certainly required. We have a new era of entrepreneurial investment. That is exceeding what went on even in the early aircraft business. These entrepreneurs, Blue Origin, SpaceX, and many who are somewhat smaller are applying many of the lessons of Apollo, particularly in emphasizing the importance of having young people in their organization doing most of the work. Now, lunar resources, I think, are best developed privately and in parallel with other requirements driven by national interest. Now, whether the private sector does the whole 9 yards, as I propose in my 2006 book, Return to the Moon, or whether they take advantage of the launch capabilities of the government is an open issue. But nevertheless, I think when you actually get to the development and exploitation of the lunar resource base, you better depend on the private sector, properly licensed and regulated, to do that job. The government will never do that job very well, believe me. Conclusion, it was no accident that Apollo was successful. Just remember, a Saturn-enabled mission launched every 2 months in 1968 and 69, and it resulted from a management environment that worked. Now we're talking about maybe launching an SLS every 2 or 3 years. It's almost unbelievable. Don't reinvent the past, but for God's sakes, learn from it. The physics of spaceflight does not change yet. You never know what's going to happen. But right now, we have to deal with the same physics that Apollo did. If the concept worked once, check them out for modernization. With that, I will close, and I think we're out of time.
Jack, thank you very, very much. Everybody in the room thinks you ought to run for Senate again, so you can get these words up to the powers that be, and we really appreciate your service on the committees related to the Space Council, et cetera. I wonder if you would, just to capture the spirit of Apollo again, I wonder if you could just take a minute to maybe relate the story that we, sort of our kind of like shenanigans in trying to get a far-side landing in Apollo, and how that illustrated at least the ideas that were going around for really optimizing the Apollo system.
Well, this really took off after the Apollo 13 accident. We had, a bunch of us would meet in my apartment, refer to ourselves as the Lunar Mafia, and explore all sorts of crazy ideas. And at that time, it looked like we needed to do something to excite the American public and the politicians enough to make sure that we continued the program. And the whole program, I mean, it might have been canceled after Apollo 13. And so the thought was, out of that group, that we come up with a list of four places on the moon that everybody always wanted to go to. And that the missions be put together starting with 14 to, at that time we thought we didn't know how many more missions might be flown, but starting with 14 that would go to those kind of places. Those places included Tycho, far north, far high latitude site, the near part of Orientale Basin on the west side of the moon, and the far side, culminate in the far side as a way of exciting everybody. That, we had a lot of fun with that. Never went anywhere, of course. But when Apollo 17 came up, it looked like another opportunity to look at the far side. And so the Lunar Mafia, among their other activities, began to think about how you would implement such a far-side mission and still maintain communications. And one of the team, one of the mission control guys, knew about Tyro satellites that were on the shelf, I believe at TRW at the time. And he investigated that and found that we could get 2 Tyro satellites as communication satellites to put in L2 for the mere cost of, in those year dollars, of $80 million. That was part of the plan, and then some of the mission control guys, mission planning and analysis group that you knew very well, Jim, MPAD, they unfortunately started to use computers in the flight directorate to work out the trajectories and the orbital mechanics and stuff like that. And the first thing I knew about it was John Llewellyn, who was involved in that, came to me and said, "We're in deep trouble." They found out we were using the computers. And so I had to go over and apologize to Team Kranz and try to pull Llewellyn's chips out of the fire for having used government property, computers for those analyses. But I think the real problem with that idea at the time that I didn't recognize, and I often miss these kind of clues, is NASA was tired. The major managers of NASA had been at this thing for really a decade, sometimes longer, and I think they really did feel that they had dodged a bullet, and not having a major accident, losing a crew. And so the last I heard of the far side landing for Apollo 17 was a chance meeting in the halls of Building 1, where Chris Kraft, who was director of the center at that time, came up to me and said, "Forget it." And
Thanks, Jack.
That's the end of that story.
Well, Tsiolkovsky or bust, that's what I say, okay.
Well, now, as you know, Jim, I think, we had the capability to land at Tsiolkovsky. I don't think there's any question about that. We had the photography. I mean, that was probably, and we knew how to do landmark tracking and stuff like that. I mean, Apollo 17 flew right over Tsiolkovsky.
Mm-hmm.
Now though, I think the more exciting areas are probably, you never figure out which ones you really want to go to. It would be in South Pole Aiken.
Good choice, Jack, good choice. So we really want to thank you very much for taking your valuable time and talking to us. The students really appreciated it. We'll probably send along a few more questions. Maybe we can arrange a telecon at some time in the future to follow up on some of those. And I want to say that this has been the perfect capstone to our course. It's really given us a vision of not only what science can be done on the moon with humans and robotic exploration, precursors and postcursors, as it were, but it's also given us an idea about the kind of resolve we have to make this a reality. So we deeply appreciate you taking the time to do this. And I also want to thank the people at the Solar System Exploration Research Virtual Institute, in particular Ricky Guest for his capabilities in getting us to log on and link in every time. So Jack, we deeply appreciate it very much, and thank you.
Well, thank you. Let me add my appreciation, Jim, to what you and Dave have done, and Ricky, and everyone who has made this course possible, and certainly my participation today. It's really great that you're working with the next generation, and let's see if we can give them some real opportunities.
Sounds great. Okay, Jack.
Take care.
Thanks. Okay.